Okay, welcome everybody. So let's continue taking a look at some examples of sets of objects along with operations addition and scalar multiplication to see whether they satisfy the axioms for a vector space. So in this video, we'll consider V, our objects are going to be vectors in R3. And so if we use the regular vector addition and scalar multiplication, this is going to be a vector space. But what we'll see is that whether or not something is a vector space doesn't just depend on what objects you're thinking about, but also the operations you define between those objects. So here I'm going to change, we're going to use the regular scalar multiplication that we have for vectors, but I'm going to define addition of two vectors in the following way. U, which is U1, U2, U3, plus V, which is V1, V2, V3. When I add these two vectors, rather than add them component-wise, I'm going to define addition in this way, where I'm going to just take the second component of the vector V and add that to U1, U2, and U3 to get the result. So here, we're not taking U1 plus V1, U2 plus V2, U3 plus V3, but rather we're adding V2 on to each of the entries in vector U. So let's see what happens if we define addition, vector addition in this way. So is this going to be closed under addition? Yes, that is not going to be a problem because I'm going to wind up with a vector that consists of three real numbers. So this is going to be located in R3. So by defining this sort of vector addition, we still are closed under addition. The sum of any two vectors is going to result in another vector in R3. The next property is the commutative property for addition. And so here, just for the sake of saving some space, I had to write these vectors as row vectors, but you really should be thinking about these as a column vector here. So I'm thinking of U and V as two column vectors, and then their result is a column vector. This is the entry in the first row, in the second row, and in the third row. I've just written it out as a row for space reasons. So if I take U plus V, then by this definition of addition, I would get U1, V2 as the first one, U2, V2 as the second entry, and U3, V2 as the third entry. If I change the order that I add vectors, now I'm going to get V1 plus U2 as the first entry, V2 plus U2 as the second entry, and V3 plus U2 as the third entry. And this will work for some vectors U and V, but it is not going to work for all vectors U and V. So these properties need to hold for any pair of vectors U and V that I pick in my space, which in this case is R3. So this is not going to hold. So this would be enough right here to just stop and say this is not a vector space because all of these properties need to be satisfied. And here is one of the properties that we have shown is not satisfied. So since this vector addition is not commutative, this vector space, this collection of vectors along with these operations is not a vector space. But for the sake of considering these properties, getting used to these properties, we can check some of the other conditions. I will kind of just leave them here for reference rather than go through them in more detail. But the associative property is actually satisfied. When it comes to looking at the zero vector, here you can see that we actually have different types of zero vectors that we could use. So for example, if I had a zero vector which had something here, 0 in the second position, and something over here, and I add this to any vector U, since when I add this on, we're only going to add the second entry in this vector, this would actually satisfy this property. And there are other vectors that would work here. So we actually do have a zero vector here. The issue is we don't have one of them. We have an infinite number of zero vectors. And then looking at the additive inverse, not every vector U in this space has an additive inverse. So for example, if I had a vector u, which consisted of first entry 1, second entry 2, third entry 3, there's no way that I could add some vector v to this using this definition of addition and get the 0 vector back. And so when I mean 0 vector here, I mean 0 vector in our typical sense, since this is really not what we would want to think as a 0 vector, which is why this operation is kind of weird. So if I had a vector like u, which was 1, 2, 3, there's no additive inverse in the sense that I couldn't get the 0 vector where it has all 3 entries equal to 0. And if we want to explore these other operations, again, we've already determined that this is not a vector space because of the commutative property of addition. But this scalar multiplication, we're using the usual scalar multiplication. So this is closed under scalar multiplication. So if I take c times any vector u, we will indeed get a vector in R3. The distributive property, the first distributive property is satisfied. We can check that over here. However, the second distributive property, which is saying that if I have a sum of two scalars c plus d, and then I multiply by a vector u, well, on the one hand, I would get c plus d times u1, c plus d times u2, c plus d times u3. If I compare that to what I would get if I take c times u and then add that to d times u, because we have this kind of unconventional addition where I'm only adding the second component of the second vector, this property is not going to be satisfied. So one of the distributive properties is satisfied, but the second one is not. And then we have a couple of other properties. This property, the associative property for scalar multiplication, that works just fine, as well as the identity, multiplicative identity. When I take 1 times u, we haven't changed our scalar multiplication. We would get that back. So here we can see some of these properties hold, some of these properties don't. The main one is that addition is not commutative. That throws off some weird properties about the 0 vector as well. So this vector, this set of vectors with these operations in particular, this kind of unconventional addition, would not satisfy all of the axioms for a vector space.